Welcome to Excel 2013 Statistical Analysis video number 28. Hey, if you want to download this workbook or our PDF file, click on the link below the video. Hey, we're over here on the sheet CP. We're going to talk about multiplying, but we first got to talk about conditional probability, then independence, then we'll talk about our multiplying law for probability. Now, conditional probability, just as the word condition implies, there's going to be a probability, but there's a condition first. And our notation will be, hey, what's the probability of A given that B has already occurred? So the condition is going to be the fact that something has already occurred. One of the keys to figuring out conditional probability is realizing that after the first event has occurred, the sample space has changed. Now, we've talked a lot about sample space and sample points. And let's just think of an example. Here's our probability we're trying to calculate. What's the probability of pulling one queen without replacement? And that means we're not going to put it back in the deck. Well, this is not a conditional probability. This is classical. We can simply say equals, well, how many queens are there? 4. Divided by how many cards are in the deck? 52. So enter. So the probability is about 7.5% that you can pull a queen, right? If you have the 52 card deck. Now, the next question becomes, what's the probability of pulling a second queen given that you've already pulled the first queen? Well, the sample space has changed, not only in the denominator, but in the numerator. So there's only 51 cards left. And we already know that something's happened. We've already pulled a queen. So once you have the queen in your hand, now for this second event, you can calculate with a new sample space. -1 queen. 3 divided by 51. That's the probability pulling a queen this time. Now we can still do this again. We could keep doing this. What's the probability of pulling a third queen given that you've already pulled queen 2 and queen 1? How lucky are you? Now, this has nothing to do with in succession. We'll talk about that later. We'll definitely calculate the probability of these 3 in succession. But each one of these are individual. We're just talking about what a conditional probability is and learning that the sample space has changed. So 50 cards now. There's only 2 queens left. So the probability this time, once you already have the 2 queens in your hand, 4%. Conditional probability. Now let's scroll down and look at another example. So often what we're given in this class and in many situations, we're given a cross-tab table. So remember, the intersection is always and. The outside is one condition. This is all counting. There's the grand total. Now here's our payment methods from a particular convenience store. And here's the amounts. And we've already calculated the cross tab. So if I click right here, that means 8 people out of 200 used a debit card and paid greater than 75 bucks. Right here, 21 out of the 200 records in our original data set, the person used cash and spent between $0 to $25. All right, so now we want to calculate some probabilities and then introduce conditional probability in the context of a cross-tab table. So our first question will be, hey, what's the probability of randomly selecting a person and finding that they paid cash? Hey, I'm going to say equals, oh, here's the cash total out in the margins, and I'm going to divide it by the total and enter. So 22%. Now, our next question is, what's the probability of finding someone that paid cash and the transaction was for greater than or equal to 75 bucks? Hey, this is and, so I'm going to get my count for 2 conditions, cash and greater than or equal to 75. And I'm going to compare it, division, to the grand total. Enter. Now, this is our first conditional probability calculated from a crosstab. And our question is, hey, what's the probability of finding someone that paid cash given that the transaction was for 0 to 25 bucks? Well, wait a second. What are we going to do? This given that paid 0 to 25 bucks, that means we're isolating on this column. So the sample space went from 200 to 63. Now we can simply say, out of all of these 63, what's the percentage for cash? 21 compared to 63. So when you're doing a conditional probability from a crosstab, you say equals the count for the and, cash, and 0 to 25, divided by, for in this case, the 0 up to 25 total, or our marginal total. Enter 33.33%. Now this is from a crosstab where we had our count or our frequency. Let's look at the same example, but crosstab where everything's expressed as a percentage of the grand total. Now back in chapter 2, we saw cross-tabulated with percent of grand totals. In this chapter, they call this a joint probability table. Each one of the intersecting cells shows us and probability. The event is credit and 0 up to 25. The margins over here, the event is a single event, $50 up to $75. Over here, the single event is cash. So what's our probability of finding someone that paid cash? Equals, they already calculated for us. It's out in the margin. It's a single condition. Enter. Probability that someone paid cash, and it was for greater than or equal to 75. They've already calculated for us. That count from the table up there was already divided by the grand total, but they already did it for us. There it is, 1.5%. Now, probability that someone paid cash, given that the transaction was for 0 to 25. Well, up here, remember what we did? We took 21 count, that's an and count, and divided it by the sample space has changed 63. Well, guess what? That same concept of and divided by marginal, we're just going to use the percentages. 10.5% divided by the 31.5%. Enter 33.1/3%. So when you're calculating conditional probabilities from a joint probability table, it's the and divided by the marginal. Now, one last example for conditional probabilities. The textbook doesn't show this, but we did it in Chapter 2, cross-tabulated with percent of row totals. So each one of the numbers in this column are being expressed as a percent of the grand total. When we get over to here, these percentages have nothing to do with that grand total. It's just the total for greater than or equal to 75. So 53.6% of the transactions that were greater than or equal to $75 were done with a credit card. 10% done with cash, and like 7% for a check. The point here is that these are all conditional probabilities. All right, now we need to go over to our PDFs and look at an example for conditional probability. Alt-Tab. I want to talk about tree diagrams, because sometimes you'll see conditional probabilities in tree diagrams. Now, this was a survey done for people over 50, and 2 questions were asked. Did you have a heart attack? Yes or no. The next question was, what type of smoker were you? Did you not smoke? Were you moderate or heavy? Now, earlier in this chapter, we talked about outcomes. Notice there's 2 outcomes here, no or yes. Once we get to no or yes, then we have 1, 2, 3. So we could calculate the total number of outcomes. 2 times 3, that would be 6. But notice that here, once we get to no, the original count was 500. Of that 500, 320 people said they did not have a heart attack. So once we get to this conditional probability, the sample space has changed. 320, 320, 320, the denominator in all of those. So of those people that said no, there were 220 that said they didn't smoke, 65 moderate, and 35 heavy. Down here for the yes, oh, look, of the 500 people, 180 said yes. So when we get to our conditional probabilities, 180, 180, 180. So of this group, we've isolated, not the original 500. The sample space has changed. Of the 180, 30 said no, 60 said moderate, and 90 said heavy. So like half the people that says yes, they had a heart attack were also heavy smokers. Conditional probabilities. By the way, when you multiply the margin times the condition, you get a joint probability. This is how you do it in a tree diagram. You can see here 320 divided by 500. Whoop. And then for this particular one, not smoke, we took our 220 divided by 320. Notice that if you were doing this longhand, cancel. So you really take whatever the and was. That's the count for I did not smoke and I did not have a heart attack, and compare it to the 500. Then you get your joint or and event probability. All right, so conditional probabilities here. Now we want to scroll down to page 25 here and talk about independent events. Two events are independent if the probability of one event is not affected by the occurrence of other events. If you think back to your queen example, the second probability was definitely affected by the first event, so those were not independent. Now, our rule of independence will be this. If the conditional probability A given that B already occurred is equal to A, then the event is independent. And that makes sense because guess what? Probability given that B has already occurred. Well, if B has no effect on A, then of course these two have to be equal. B has no effect on A. You could do the reverse. Probability of B given that A has already occurred. Well, if A has already occurred and there's no effect on B, then these two have to be equal. If the events are not independent, we can call them dependent, like our queen example. This second probability is dependent on the first. Examples of independent events: rolling a 6 with a die does not affect the next roll. A traffic jam today generally does not affect whether you are in a traffic jam tomorrow, meaning you didn't get in some horrible accident, right? You're just sitting in traffic, right? That's not going to have any effect on tomorrow. And we'll do calculations on probability of getting in traffic later in the class. Whether or not Google stock goes up does not affect whether or not Whole Foods stock goes up. Those two events are independent. Now I want to scroll down and just briefly look at our multiplication law because, oh, multiplication is going to be and. Whereas adding was or, multiplication is and. And how do we calculate an and? In this textbook, they use the intersector symbol, and there it is, to calculate probability of A and B, or A intersect B. It's the probability of A times probability of B, given that A has already occurred. So for our queen example, we just will multiply those, and that'll tell us the probability of pulling queens in succession. We could similarly get the same exact answer, probability of A and B, if we have probability of B times probability of A, given that B has already occurred. Now, we just talked about independence. What if B has no effect on A? Multiplication law for independent events, then you just multiply the two. Like we'll have the probability of Google stock going up and the probability of Whole Foods stock going up. So we'll multiply, and that will be the probability that both go up. Now here's a big hint here. And there's the intersector operator. And is always multiplying. Or there's the union operator. It's always adding. It's exactly the same in Excel. Every formula you create where you're manually doing and criteria, or you're going to have to use multiplying or addition. Now let's go over to Excel, and I want to go to the sheet multiplying. Here's our rule for independence. Here's our rule for multiplying. Let's scroll down and look at an example. Here's our queen example, right? We calculated the probability of pulling one queen without replacement. Boom, that's for a single event. Then once we knew that we picked a queen, we calculated the probability, hey, pull a second queen, given that we pulled the first queen. Notice that's for this single event. And then finally, what's the chance? We already know there's two queens already pulled. The sample space has changed. 52 cards, 2 of them are queens. The probability is 0.04. But now the question is, how do you calculate pulling these 3 in succession? Hey, the multiplying rule. Let's first calculate the probability of pulling 2 straight queens. Notice our rule, this is and, multiplying is and, simply probability of A times probability of B given that A has already occurred. So it's simple multiplication. There's A, there is B given that A has already occurred, and enter. Wow, so the probability is 0.004. That's less than 0.5%. Now the probability of pulling 3 straight, you got it. A times B given that A has occurred times C given that A and B have already occurred, and enter. Wow, look at that, 0.00018. Very small probability that you could pull 3 straight queens. And there's these two expressed in probability notation. We can have 2 ands, we can have 3, we can even have whatever number we want. Now notice for this example, there was only one sample point. And we could list the sample point for each one of these. The sample point for this one would be queen, queen. That's it. There's no other possibility, no other sample point. This one would be pull a queen, then a queen, then a queen. Now, I want to look at another way of calculating this single sample point. Now, notice here we used formula inputs, but we did 4 divided by 52, 3 divided by 51, and 2 divided by 50. Now, I actually want to do a formula where we hard code the numbers right in, because sometimes with these card examples, it's helpful to do it this way. Hey, our first probability was pull a queen without replacement, so we had 4 queens divided by 52. That's the first one. And we're figuring the probability of pulling 3 straight. So we multiply. And what was the next one? Well, we already pulled 1 queen, so there's 3 left, and there's 51 cards. And then we finally multiply. And the third probability, well, there's 2 queens left and 50 cards. So that way, we've actually hard-coded it right in. When I hit Enter, of course, I'm going to get the same input. Now, we want to go look at another question. I actually want to calculate the probability of pulling 2 queens in 3 tries. But this means we're going to have a bunch of sample points. So I want to first concentrate on asking a very specific question. This is not only pulling 2 queens, but I want the order just like this. I want to say in step 1, I'm pulling a queen. The next pull, I'm not pulling a queen. And then finally, I'm pulling a queen. So how in the world would we do that? Well, we got the first one. Equals, well, there's 4 queens divided by 52 times. And now how in the world do we calculate not a queen? We're going to do some counting. And you can count on your fingers if you have to. Well, we know that we started with 52. We pulled 1. So 51 will be in the denominator. That's not hard. It's the numerator. Well, wait a second. There were 52. We pulled 1. So that would be 51 cards total. But remember, this is asking the question, not a queen. Well, there's 3 queens in that 51, so we subtract 3. That's the numerator divided by 51. Now, the third probability times, well, we just subtracted 2 cards, so we know in the denominator it'll be 50. But what's up in the numerator? Well, there's 3 queens left, so 3 divided by 50. All right, so sometimes when you're calculating probabilities, you really have to think about it. Enter, and there we got for this particular sample point, 0.004344. Now we want to come down to pulling 2 queens in 3 tries. Well, that means we're going to have to list out our sample points, which I did here. We could pull a queen, then not a queen. We could pull a queen, not a queen, then a queen, and then not queen, queen, queen. So we have to calculate the probability for each one of these. And these are conditional probabilities for each one of these sample points. So the first one, hey, equals 4 divided by 52. We pulled a queen, so then it's 3 queens left divided by 51. And finally, we get not a queen. In parentheses, we have 50 cards left minus the 2 remaining queens. That's in the numerator divided by 50. Boom, there's our first probability for that sample point. Now, each one of these is going to come out exactly the same because it's multiplying. But as we're building our understanding of how probability works and sample points and events, I'm going to actually list it out exactly as I see it here. So this one equals, well, 4 divided by 52 times not a queen. So in the numerator, I know there's 51 cards left, minus the 3 queens. That's not a queen, divided by 51, times, and I'm left with 3 divided by 50. Enter. Oh, it's exactly the same. But let's try and calculate this one just as we see it here, NQQQ. So NQ is, well, 52 total cards minus the 4 queens divided by 52 times, well, there's still 4 queens left, so 4 queens divided by 51 times how many queens left? 3 divided by 50. And I see I got an extra parentheses here. Enter. And there we have it. Now with our 1, 2, 3 sample points, we can use our definition of calculating a probability for event. This is the event. Pull 2 queens and 3 tries. We're going to add all the sample point probabilities. Alt equals, it guesses wrong. I highlight down here, and enter. Wow. So 0.013. So 1.5% chance that I could pull 2 queens in 3 tries. Now, this is multiplying conditional probability. Next chapter, chapter 5, we'll talk about discrete distributions, and hypergeometric distribution is one of them. So there's a hypergeometric distribution function, which will calculate this given these inputs. And this distribution and this function are perfect because this distribution assumes that the events are not independent. And the probability changes each time. All right, so we're going to use the hypergeometric distribution function equals HYP, and I'm going to arrow down HYPGEOM.DIST. Now it has 4 inputs. Sample successes, that means the number of queens we're pulling, 2. Comma, number in the sample, we have 3 tries. Comma, population successes, there are 4 total queens, comma, and the number in the population, 52 cards, comma, and the 5th argument, we have to choose cumulative or probability mass function. The probability mass function for discrete distributions calculates the individual probability. So I'm going to use false or 0. So later, as we go through this class, we're going to see cumulative distribution and probability mass function for all sorts of distributions. You can use true or false or 1 or 0. I'm going to tend to use 0 and 1. But it's absolutely OK to simply double click and take that from the drop down. I'm going to put a 0 and enter. Wow, look at that. It calculated it perfect. Probability, pulling 2 queens in 3 tries. Now we want to go down and continue to talk about our multiplication rule. Hey, we want to calculate the probability that Google stock and Whole Food stocks will both go up next year. Well, if the probability of Google going up is 0.35 and probability of Whole Foods going up is 0.2, these are assumed to be independent events, right? Because what's going on at Google generally is not going to have any effect on what goes on at Whole Foods. Here we go. We're simply doing straight multiplication. 0.35 times 0.2. That's a lot easier given that these are independent events. So it's 0.07 that both will go up next year. Now let's go look at our next example. Example number 4. We want the probability that 3 straight products off an assembly line are defective. Now from past data, they've determined that about 2% of the products are defective. So this is assumed to be an independent event. So when we get to multiplying, we simply, for our probability of 3 straight defects off an assembly line, we simply multiply 1, 2, 3. Enter. Wow, that's unbelievably small probability. So if we actually did see 1, 2, 3 rolling off the assembly line, we know there's trouble. That probability is just too small. Now let's ask a slightly different question. And when we asked not 1, 2, 3 all in a row, but probability 2 out of the 3 products off the assembly line are defective, we're going to have to deal with sample points. Now here's our given probability. So if we know this, That means at any particular time, the probability of not being defective, remember, this isn't either or, it's one or the other. We simply use our complement rule. Equals 1 minus our 2%, and we get 0.98. So our goal is to calculate 2 defects in 3 tries. Well, let's come down to sample points. Defect, defect, not. Defect, not a defect, defect, not a defect, defect, defect. Now again, we did our conditional probability sample points up above. That was a lot harder than this is going to be, because here we simply say equals the probability, and since they're independent, we take the probability times this 0.98. That's for the D, not D. Now again, these are all going to be the same, but I'm emphasizing how these sample points are constructed. So we have defect times not a defect, boom, times a defect, enter. This one is not a defect times defect, defect. There's all of our sample points. The definition of probability for event is to add up all of the probabilities for all of the sample points. Alt equals, highlighting, and enter. Now this actual event fits the definition of a binomial distribution. That's what we get to do next chapter. But here we're going to see how to calculate for this particular probability. And I can see that I forgot Control-C, Control-V to put what we're calculating here. Equals BINOM.DIST. And there we have it, tab. Now we need the number of successes we're after. That's 2 defects in 3 tries, comma, trials or steps in our multi-step experiment. We have 3, comma, and the probability of success, which remains the same each time, comma, and our false for probability mass, because that's the option that calculates the individual probability. I'm putting 0, and enter. We calculate exactly the same thing. All right, our last example for multiplying. Hey, here's our example from travel survey of people who visit Seattle. We saw this last video for adding, but here's the probability that they visit the Space Needle. Here's the probability that they visit Pike's Place Market. And here's the probability that they visit both. Now, events are not independent. We know that there's some overlap between these. We have a both here. Both is a synonym for and or intersection, right? So that's our and. These are our 2 individual probabilities. But now we're going to ask the question, what's the probability that we visit the Space Needle given that we've already visited Pike's Place Market? Hey, this is a conditional probability. And guess what? Our multiplication rule was rearranged so that we have conditional equals and divided by the actual B probability. Now, we saw this earlier when we talked about our crosstab tables. The inside and divided by the margin gives us the conditional probability. So here we don't have a crosstab table. We're just given the percentages. So boom, we can do this easily. Equals the and we divide it by, and we're looking over here, Space Needle, given that Pike's Place already occurred. So we pick the Pike's Place and enter. So the probability that someone visited the Space Needle given that they went to Pike's Place Market, 0.3846. Now we can do probability of Pike's Place given that they've already visited Space Needle equals the and divided by given that Space Needle. So we pick the Space Needle and enter. 0.555. Now we want to go look at another example on the sheet, and I'm going to scroll the sheet tabs ahead. Crosstab, no data set. Now here we're going to talk about multiplying and how to calculate it directly from our crosstab frequency distribution. And then we'll talk about how to do it straight from our joint probability table. So our crosstab has product along the row headers and region along the column headers. The intersecting values, of course, are adding with 2 conditions. Here's the grand total. So when we get to calculating what is the probability the quad was sold, given that it was sold in the Midwest, we know it's conditional. Now that's one way of stating it. Another way you might hear it is, if a product was sold in the Midwest, what is the probability that it was a quad? In either case, we're limited to items sold in the Midwest. It's not the grand total we're talking about. It's just the Midwest in that total right there. So we'll compare the quad amount to the Midwest. Quad, given that it was in the Midwest, equals the number of units sold for quad in the Midwest, that's and, divided by the changed sample space, just the items sold in the Midwest, and enter. 49.37% probability that a quad was sold, given that it was sold in the Midwest. Now what about and? What is the probability that we sold a quad in the Midwest? That's clearly an and. Guess what? Equal sign. We already calculated counting with two conditions. But when we do our division, we're going to compare it to the grand overall total. Enter. So 17.47%. Example number 3. What is the probability that we had a sale in the Midwest or the sale was for a quad? So this is an or situation, quad or Midwest. Now, if it's something like quad or tri-fly, that would be a mutually exclusive event. But there's definitely some overlap here. So when we, in the numerator, we're going to take all of the quads, boom, plus all of the Midwest, minus the overlap, the and. We don't want to double count. Close parentheses, and we compare this to the overall grand total. So when we hit enter, the probability is 53.46%. By the way, those were pre-formatted, right, with percentage number formatting. Now, this is crosstab with a frequency distribution. That means count. What if we're given our joint probability table? That means every percentage is calculated off of the grand total. So our question is, what's the probability of quad given that it was in the Midwest? Remember, we say equals the and divided by the marginal. We have percentages here, but this is the same formula we did just above with the actual straight count. And enter, 49.37%. Now, what is the probability that we sold a quad in the Midwest? This is that and. It's already done for us. This is the joint probability table equals, there it is, enter. And now our or, same thing. We're going to have to add, subtract. Whatever the first marginal percentage is plus the second marginal percentage, and subtract the and. So here we go. Quad or Midwest. There's some overlap. Quad plus Midwest, and subtract the overlap. We do not want to double count, and enter. So 53.46%. All right, hey, this video was all about multiplying probabilities. We saw how to do conditional and or straight from a joint probability table, straight from a frequency distribution, cross tab. Back over on multiplying, we saw how to calculate conditional probability using the multiplying rule. We saw how to multiply if the events are independent. For our queen example, we saw how to multiply when the events are not independent. There's our multiplying law. We talked about independence, and we even back over on CP talked about conditional probability. All right, next video will be our last video for Chapter 4, and it will be a comprehensive video where we look at multiplying and adding. All right, we'll see you next video.